Nice. All right, more NP-complete problems and some nice reductions. So let's recap NP-completeness, say a few more things. So NP is a set of all languages which have non-deterministic polynomial time algorithms, and the way that I'm using this notation, but what we saw is the definition using certifiers and certificates. We defined the notion of NP-complete problems, right? When is a problem NP-complete? It's the hardest problem in NP, right? How do we define that? We say the problem is NP-complete. First, if it is in NP, it's in the class, and every problem in NP reduces to it in polynomial time, right? So for every language L prime in NP, L prime reduces to L in polynomial time. So what that means is that every problem in NP can be solved in polynomial time if and only if L can be solved in polynomial time. So it's a sense that this is a important problem in NP because it's a hard problem in NP. Okay, so there is a notion of NP hardness. What does it mean to be NP hard as opposed to NP complete? A problem is NP hard if every problem in NP reduces to L in polynomial time, right? So what this means is that we are not insisting on this property. So in particular, we don't know if this problem is in NP. It could be outside, right? So pictorially, okay. So before we go to that, we know that Cook-Levin theorem says that SAT is NP complete, and via reductions we can prove many other problems are NP complete. But pictorially, what is the difference between NP complete and NP hard? So P is the set of all problems that we can solve in polynomial time, and P is a larger class. We don't know what it is in the sense that we have a definition based on certifiers and certificates. So, and it's easy to see that NP contains P, and you want to understand NP. And a class of this NP, a subclass of NP, is NP complete problems, right? If a problem is an NP complete, means that every problem in NP reduces to that problem. What does it mean to be NP hard? NP hard could be a problem which is outside NP, but every problem in NP reduces to NP hard problem, right? It doesn't have to be in NP. That's the only difference between NP complete and NP hard. Okay? That makes sense? So we are dropping this condition that it is in NP. So it could be outside, and you may not know whether it is in NP or not. Does that make sense? Yeah? Yeah? That's the difference. Okay. And so to prove that something is NP hard, all you have to do is take an existing NP hard problem and reduce it to your new problem. You don't have to prove that it's in NP. That's the only difference. You omit one step. Okay? And so let me make some interesting comment. You may think, okay, look, what is the state of the world, right? We don't know, because we don't know whether P is equal to NP or not, right? It's okay. So okay, these are two possible scenarios. If P equal to NP, everything collapses to P. That's one scenario. What about if P is not equal to NP? Well, that's an open question, but we can ask, if P is not equal to NP, let's say hypothesize, is every problem that is not in P NP complete? Okay. So more pictorially, you can ask, we don't know if this big circle is equal to the small circle, but suppose the big circle is not equal to the small circle. Is there any problem here? What does it mean? This problem is in NP, outside of P, but it's not NP complete. Does that make sense? The question, right? Can there be a problem outside P which is not NP complete? Yeah? And so you can say, how would you know, right? In the sense that we don't even know that the whole thing is one. But you can prove the following, and this is a famous theorem of Ladner which says that if P is not equal to NP, actually there are many problems in between. Okay? So if in fact, so conditionally, if suppose P is not equal to NP, there will be problems here which are not NP complete. Okay? So they're not as hard as NP complete problems, but there will be there, right? It turns out that we don't know any natural problem in that category, right? All the interesting problems that we study happen to be either NP or NP complete. Why is that? What is natural? I don't know, right? So that's another mystery. Why is it that we don't encounter problems which are neither in P nor NP complete? No idea. Okay, right? So the complexity theory studies this very intricate things, and it's well beyond the scope of this class. But just some background. So, okay, today we're going to see 3 problems, and these are all, important problems both from a theory and applications point of view and for reductions. And these are all NP complete, and they go back to Karp's original paper in the late 70s, where he proved a whole bunch of problems are NP complete. And the reductions are very complicated in some sense, in the sense they're very complicated to come up with, right? They're very beautiful, and what I will do is I'm not going to be able to formally nail down all the proofs because it takes time. I will simply sketch to you the ideas, and you can kind of convince yourself that yeah, that makes sense, right? And our goal is not to fully understand each of those proofs because they are quite intricate, but our goal is to know that these problems are actually NP complete so that we can use them in other problems as reductions, right? So, but to see how intricate the problems can get. Okay, so we'll see the first problem is NP completeness of Hamiltonian cycle problem. What is a Hamiltonian cycle problem? Well, it can be defined both directed graphs and undirected graphs. We'll work with directed graphs because it makes life a little easy. Directed graph, and what is a Hamiltonian cycle? It's a cycle which visits all the vertices, right? It's a cycle, it's not a tour, right? That means the cycle has to visit a vertex only, come in and go out, right? This is a Hamiltonian cycle. And the question is, given a graph, does it have a Hamiltonian cycle? Yeah? Directed? Okay. Okay, it's not obvious how to solve this problem. What we're going to show that, Hamiltonian cycle is a hard problem by reducing 3-sat to Hamiltonian cycle. Yeah? Okay. Again, the interesting thing is that how can it be that this satisfiability problem can be reduced to this graph problem, right? What do we need to do? To do this reduction, we need to take a formula, a 3-sat formula, right? The reduction should create a graph, right? Such that the formula has a satisfying assignment if and only if the graph has a Hamiltonian cycle, right? Okay, so again, it's always a little tricky, like how do we convert formulas into formulas into graphs, and how can we encode satisfying assignments in formulas into Hamiltonian cycle? And so again, I start with the formula phi, and I have to create a graph. And okay, we assume that phi has n variables, right? Or not assume, let's assume that we're given a formula, the algorithm or the reduction has to produce a graph, right? So it has n variables and m clauses, and remember it's 3-sat, right? Okay, so this is the starting point, right? It's always important to figure out how are we going to encode satisfying assignments, right? As objects as Hamiltonian cycles, right? So let's look at this graph, okay? Okay, how does this graph look like? It has one vertex here, one vertex here, that's easy. It has many paths. How many paths? One per variable in the formula, okay? So in this graph, this example, my formula has 4 variables, x1, x2, x4. I create this graph with 4 paths like this, okay? Okay? Okay. Now, what is this path? These edges are bidirected. That means actually there are 2 edges, one in each direction. Yeah? All right? This is a shorthand for saying there are 2 edges here, this way and this way, both directions. Yeah? Okay, is this graph Hamiltonian? Yeah? Okay, how many Hamiltonian cycles are here in this graph? So I have to start here, right? What do Hamiltonian cycles in this graph look like? So one option is I go here, right? Then I can go all the way here. I can come here, go all the way here. Come here, go all the way here, come here, go all the way here, and come here and go back, right? Okay, but I can do this, right? I can come here, go all the way here, I can go here, come here, right? And go. So my claim is that I have 2 to the 4 Hamiltonian cycles in this graph. Okay, what are those Hamiltonian cycles? Each path I can go either left to right or right to left. Yeah? Okay, because this path, once I start going this way, I can't go back, right? So I have to, the only choice I have is from here, should I go left or right, right? And once I'm here or here, I can either, I mean, if I don't traverse this path, I'll be stuck, right? So if I go from here to the left, my only choice is to go through this path from left to right. If I go here, I have to come right to left, right? Once I traverse this path, I have a choice. Should I go down and go this way or come here and go this way, right? Okay? All right. So this graph has 2 to the n Hamiltonian cycles, which corresponds to what? 2 to the n possible assignments to the variables. Okay? Does it make sense? These are, I'm putting them there so that we know that this is 1 per variable. You know? Okay, this is just a graph, right? Yeah? So right now we see we already encoded in some ways assigning, think of going left to right as assigning true to that variable and right to left as false for that variable, right? Yeah, so there's a mapping between Hamiltonian cycles in this graph and assignments to the variables, right? Yeah? Okay, but that's what the first step, right? We did that. But there's no clauses here. I didn't put any clauses here, right? Yeah? Okay. Okay, so my formula has only 2 clauses because it's very hard to draw this graph, right? So, but the idea should be clear, right? Okay, so for each clause I create a vertex, okay? So I have only 2 clauses in this formula, that is my formula with 4 variables, yeah? So I first create this graph, now I'm trying to add more stuff to the graph, right? So this box represents 1 vertex, yeah, with the clause inside, yeah? Okay, now I have to add some edges to it, right? Okay. Now I haven't told you how many vertices are there in each path, right? It didn't seem to matter, right? I need how many, this is again for simplicity to make the reduction easy to see. It's not necessary from the most efficient way. The number of vertices on this each path will be 3 times the number of clauses, okay? It's a long path, okay? Why do you need 3 times the number of clauses? I want to reserve 3 per clause. Okay, this is to make the life of to make us understand the reduction more easily. Okay, you don't need this big path, but for simplicity, let's assume that each path is so long that I can reserve 3 per clause, 3 vertices on each path per clause, because it's 3 times m, right? Okay, okay, okay. So this clause has these 3 variables, and this clause has these 3 variables. Yeah. And I only have 2 clauses. If I have more clauses, my path will be longer. Yeah? Okay. Now I need to connect this vertex to, I will connect this vertex only to the paths of the variables that occur in this clause. Okay. How will I do that? Okay. These are, I only need 2 vertices, but these are buffer vertices, which will make again the proof a little easier. Okay. I only need 2, but okay. Okay. So what I'm going to do is, look at this vertex, it has x1, and so I will connect this vertex to the path representing x1. In what way? How can I satisfy this with x1? If I can satisfy the clause with x1 if I set it to true. Okay, but remember our idea of going left to right is true and right to left is false. Okay, so what I will do is that I will say, okay, if I want to satisfy this clause by this variable, I should visit this clause while visiting this path. That's my idea, right? So I will add an edge from this path to this vertex and an edge from here to here and an edge from there to here. Okay. The idea is that when I'm going left to right on x1, which means that x1 is true, I can go to this vertex, come back, and keep going. Okay. Remember, a Hamiltonian cycle has to visit all the vertices, right? I added some 2 new vertices. When can I visit this vertex? Well, I'm saying that imagine that I'm going on this path left to right. I can go to this vertex, come back to the path, and keep going. Yeah. Okay. But remember here, x2 isn't false, right? It's not x2. How will if I want to make this clause satisfied by x2, I have to set x2 to false, right? x2 to false means I will be, if I want to set x2 to false, I will have to traverse this path right to left. Okay. So I will add a edge from here to here and there to here. Okay, it's a little different from x1, right? Yeah. And x4 is again, because it is true, the idea is that I can visit this while going left to right. Okay, I mean, is the construction of the edges clear? No. Okay. Okay. This is a vertex, right? That's a box, but it's actually a single vertex. Okay. And remember, I have reserved these on every path. I have reserved 3 vertices for that clause. Yeah. Okay. I connect this vertex to 2 adjacent vertices on the paths corresponding to the variables that occur in it. Yeah. Okay. I only connect it to x1 path, x2 path, x4 path. I don't connect it to x3 path because x3 is not in that. Even though they're reserved, I don't use them. It's just to make my life easy to describe it to you. Okay. How do I connect them? If it is x1, which means it's a positive literal, I connect 2 edges so that I can visit this vertex while traversing this x1 path left to right. Okay. I can't visit this vertex coming from right to left, right? You know, there is the edge is directed this way. Okay. Okay. And if it is not x2, because I would connect it at the edges so that I can visit it while coming from right to left, but not left to right. Yeah. And same with x4, because it's positive, I connect it so that I can come back. Yeah. And that's all I do. For every clause I do that. Okay. Now what should I do? You know, not x1. Not x1 is, remember, not x1 means that I should connect it in such a way that if I'm going right to left, I should be able to visit it, right? So okay, is it right? You know, see, when we're coming right to left, we can go and come back. Yeah. And not x2 is also right to left. Not x3 is also right to left. But I don't connect it to x4 because x4 is not. Is the construction clear? Yes? No? Yeah? Okay. Yeah. Oh, it's one vertex. I'm putting the box so that you can actually see what is that formula, right? Otherwise, it's hard to see what we're doing, right? Yeah. I mean, just one vertex, basically, right? You just put a box around it and put the clause in it so that we can understand how we added these edges. Is it clear? Is the construction clear? Yeah. Okay. Now the claim is this formula is satisfiable if and only if this graph has a Hamiltonian cycle. Okay. Remember, the original graph had a huge number of Hamiltonian cycles, right? Yeah. But we added now extra vertices, which makes it hard to create a Hamiltonian cycle. Okay. Remember, the original graph had a 2 to the n Hamiltonian cycles. So you can go left, right, right, right. Many Hamiltonian cycles. But as soon as you add many clauses with all these constraints, how do we know there is a Hamiltonian cycle or not, right? Right? Does it make sense? Now my claim is, if this formula is satisfiable, there is a Hamiltonian cycle. If it is not satisfiable, there is no Hamiltonian cycle. If I can convince you of that, then this construction is easy. Then you will see that if you had an algorithm for Hamiltonian cycle, you can solve satisfiability. Yeah? Okay. Alright? Now let me convince you that if this formula is satisfiable, then there is a Hamiltonian cycle in this graph. Okay? What does it mean that this formula is satisfiable? Yeah? That means there's an assignment which satisfies all the clauses, right? Another way of saying that is that for each of these, let's give me an assignment which satisfies this formula. Of course, it's a trivial formula. Sorry? Yeah, so I mean, you know, x1 is say 1, right? x2 is 0, or let's say x2 is also 1 for simplicity. x3 is 0, x4 is 1. Okay? Alright? Now, let's forget about the clauses. If I gave you this assignment, what is the Hamiltonian cycle in this graph that corresponds to it? Left to right is 1, right? You know, so let's forget about the clauses. We are imagining, I'll convince you that, okay, look, what is my underlying Hamiltonian cycle? I want to come here, right? Remember, x1 is 1, so I want to go here.
and then what should I do? I come back, go like this, right? But x3 is false, so I go like this and go like this, and x4 is 1, so I go like this and go like this. That's my intended Hamiltonian cycle, right? But this is not visiting the cross vertices yet. How can I insert the cross vertices into this Hamiltonian cycle? Right? Okay, but I know, so if this is a satisfying assignment, what do I know for each clause? That there is at least one literal which is true, right? In this case, for example, there are many choices, but let's pick one, right? X1 is satisfying this clause, right? But remember, I'm going left to right on X1 in this Hamiltonian cycle. I can visit this while going on X1, right? I can splice this in, yeah? Because I added edges to splice it in, right? Okay? So what can I do? I can go here, go up and come down and keep going, okay? So I'll modify my Hamiltonian cycle the base Hamiltonian cycle, because I picked X1 to satisfy this, and how should I satisfy this guy? There's only one choice here, right? I choose X, not X3, right? All right? So I splice it in, right? I actually, modify this and say, okay, look, I'm going to go like this, and then join this, and X3, I know I can go this, come back, I remove this edge. Yeah? Is it clear? Yeah? So for each clause, I know that there is some literal which will satisfy it and the satisfying assignment, and I'm traversing that path in the right direction for me to go up and come down that vertex. Okay, I had only picked one way of satisfying it, right? Because I don't want to visit this vertex more than once, right? I have multiple choices. For example, I could have spliced it in with X1 or X4, right? I could have visited this vertex even while going here. Yeah? I chose to go a clause can be satisfied by more than one literal, so I have a choice, but at least one should be there, right? Yeah? Does this make sense? Okay. Okay, the hard part is what? To convince ourselves that if this graph has a Hamiltonian cycle, then the formula is satisfiable. Why is that hard? Intuitively, why is it hard? Why is that not obvious? The other direction is that this, if I tell you, I start with a formula and I create this graph, and then you want to be convinced that if this graph has a Hamiltonian cycle, the formula better be satisfiable, right? Otherwise, our reduction is useless, right? How can we know that or the other way of saying this, the only way this graph has a Hamiltonian cycle after we add this clause vertices is if it is satisfiable, right? Or another way of saying it is, if you give me a Hamiltonian cycle in this graph, I will recover a satisfying assignment for the formula, right? From a Hamiltonian cycle, I need to figure out a satisfying assignment to the formula, right? If you give me a Hamiltonian cycle, okay, that is a little tricky, because why? Okay, suppose I gave you a clean Hamiltonian cycle in this graph. What is a clean Hamiltonian cycle? The clean Hamiltonian cycle starts here, and the only thing it does is that it traverses each path left to right or right to left cleanly, and jumps to a cross vertex and comes back occasionally, right, in the same path. If the Hamiltonian cycle looks like a very clean like this, from the reduction we can visualize that, if you went left to right, it means that you are going to set the clause, that variable to be true. If you went right to left, I'm going to set that variable to be false. And remember, because of the way we set up the edges, you visited only these vertices along a particular path, so I can figure out which literal satisfied each clause, right? Remember, it's a Hamiltonian cycle, so it must have visited all the clause vertices. It means that every clause was visited while traversing a variable in the right way, right? And so that should give us a satisfying assignment. Yeah? These are blue lines are these edges which the red Hamiltonian cycle is a Hamiltonian cycle in the base graph without these extra vertices, right? if you gave me this satisfying assignment and I removed these vertices, how would I think about a Hamiltonian cycle? This is how I would think about the Hamiltonian cycle, right? Left to right is 1, right to left is false. Yeah, I mean, I'm saying, I already did the direction that if the formula has a satisfying assignment, then there is a Hamiltonian cycle in this graph. I'm convincing you by saying, okay, what is the satisfying assignment? I said, okay, start with the base Hamiltonian cycle and then say, okay, insert these vertices, because you have to visit these vertices too, right? That's not the red thing is not a Hamiltonian cycle because it has not visited these extra vertices. How do you visit those extra vertices? I said, okay, look, for each of the clauses, pick one literal which satisfies it, because that's what you're saying, right? There's a satisfying assignment. And go to that vertex while traversing that path in the right direction. Yeah. Okay, and now I'm trying to prove the converse, that if there is a Hamiltonian cycle, then there is a satisfying assignment, right? That's the hard part. And I'm claiming that if the Hamiltonian cycle looks very clean like this, then you can see the assignment, right? And it satisfies the formula. The only catch is, why should there be a Hamiltonian cycle that is always clean? Right? What if I had a Hamiltonian cycle which looks like this? Can I have a Hamiltonian cycle? Here is an example, right? Then I won't know what to do, right? Okay, remember I had this box vertices, right? Okay, so I added something, right? I added some edges like this because it had okay, and so on, right? Okay, to tell you why this is tricky. Okay, it had let me see, what was that? Not x2, not x3. Okay. So these are the edges for this. So, what prevents me from having a Hamiltonian cycle of the following form, right? There's nothing prevents me. It looks like it. What if I did this? No, 1 second. No. So I'm going to try to create for you a funky looking Hamiltonian cycle which might not correspond to what okay, let's see. Suppose I said, okay, look, I came like this, then I went here, and then I went here, and actually went down here, and went here, and went there, and came down and did something like this. Okay, I don't know what else happens, right? Okay, so what I'm saying is, if I told you that this graph has a Hamiltonian cycle, and the Hamiltonian cycle could do the following, right? It came here, it went here, it went to that vertex, and then it jumped to a different path. Okay, and then started doing something here and go there and say jump there and do something else, right? How can I figure out from this weird Hamiltonian cycle that there is a satisfying assignment to the formula? Yeah? Okay, that's the point, right? The point is, I don't know, right? Okay. So, how do I know what the Hamiltonian cycle looks like? Right? What does it mean to look like? My claim is the graph is constructed cleverly so that there is no Hamiltonian cycle in this graph which is not clean. Okay, that's the point, right? The point is, if I had a Hamiltonian cycle like this, I have no information on how to extract a satisfying assignment from it. Okay. So formal claim is that if there's take any Hamiltonian cycle in this graph, right? If you visit a vertex from a path, then you have to go right back to the same path to the adjacent vertex. Okay? There is no Hamiltonian cycle in this graph where you can visit a closed vertex from one path and go to another path. Okay? All right. Why is that? Okay? Why is that the case? Okay? So that's why we created this nice buffer zones, right? So here is the thing. suppose you came on a Hamiltonian cycle and you visited this vertex, okay? If you didn't go back to it, there is no way to visit this vertex, no? So take any Hamiltonian cycle in this graph, okay? Suppose you visited this vertex using this edge, okay? And you jumped off to some other path. How will you visit this vertex? There is no way to visit that vertex, right? Because if you came here from you say, look, I could have come from here, right? But then you'll get stuck there. Because this was already visited, okay? That makes sense, roughly, yeah? So that's the idea. Okay, now the formal details of this will make a lot of time, right? Okay, that's the point of this construction, that if you visited a closed vertex on a Hamiltonian cycle and you came on this edge, you better go down on this, otherwise this vertex will not have anywhere to be visited. Okay, so all Hamiltonian cycles have to look clean in this graph. And once you have a clean Hamiltonian cycle, you kind of can see the assignment. If you go left to right on a path, I should set it to true. If you go right to left on that path, it should be false. And you must have visited each closed vertex when visiting a literal in that clause which was in the right direction. Okay? I know it's not a formal proof, but that's the idea of this, creating this buffer vertices. That the only Hamiltonian cycles in this constructed graph have this property that they have to be clean. You can't jump around like what I was trying to do, right? That is not possible. There cannot be a Hamiltonian cycle which jumps around like that. Okay? We constrain the construction. The construction is clever precisely because it made sure that you can't do the crazy things, right? Okay? Yeah, roughly. Okay. I don't expect all the details to sink in, but that's the idea. Yeah? Okay? So these are called gadgets, okay? This is very clever construction, no? Not at all obvious how to make this out of, once you see it, you say, okay, that seems plausible, right? These are called gadgets, this whole construction. So whenever you can, see, remember the reduction is from a decision problem to a decision problem, right? But really you have to map assignments to Hamiltonian cycles in such a way that you can actually take a solution to the problem and convert it into a solution to the original problem, right? The Hamiltonian cycle should tell you what the assignment is. Right? Technically speaking, the algorithm, that's how we do the proof, right? We look at the Hamiltonian cycle and say, from the Hamiltonian cycle, I can go to an assignment which satisfies the formula. The solution should tell us information, right? So we have to map that, okay? Yeah? Okay, that's all I'm going to say about Hamiltonian cycle. It's roughly what we said. Now I want to say, remember we use directions very critically in this proof, right? Yeah? We use directions very critically in this proof because, we say if you go left to right, going up and coming down corresponds to, the paths have to traverse left or right, and you may seem like directions are very important for this reduction. But I'm going to claim that the undirected Hamiltonian cycle problem is actually also NP-complete, where I'm going to reduce the directed Hamiltonian cycle to the undirected Hamiltonian cycle, which seems a little odd, right? That how can it be that, but the Hamiltonian cycle is very special because you have to visit all the vertices, and the idea is very simple. The idea is, you take, we have seen some versions of this before. Suppose, I have a graph which looks like this, right? And a vertex. I split this vertex into 3 vertices. Okay? Each vertex becomes 3 vertices. So this became, U in, U plus, U middle, okay? And all the edges become undirected, okay? So the reduction is, I'm taking a directed graph and I'm making it into a undirected graph, yeah? Right, how am I doing it? Take any vertex U, take any vertex U, split it into 3 vertices, okay? Sort of incoming U, outgoing U, and a middle U, okay? And you connect the middle U only to these 2 vertices, undirected edges. Remember, I have to create an undirected graph, right? Okay, now who should I connect? If this was V, what is this going to connect it to? If in fact this was V, what is this edge coming from? This should come from V plus, right? Remember, okay? So if this is going from V to U, I connect V plus to U minus, okay? As if I'm entering U minus from V plus, okay? So if this is W, then I connect this U plus to W, what? Minus, okay, good. So that's the construction, okay? That's it, very simple transformation of a directed graph into an undirected graph. And now my claim is that this resulting undirected graph has a Hamiltonian cycle if and only if this original directed graph has a Hamiltonian cycle. Okay? And why is that? Because this guy is going to force you to go from U minus to U plus. Okay? I mean, in the sense that of course you can say I can go U plus to U minus. What prevents me from going U plus to U minus? Nothing prevents you from going to U plus to U minus, except that you have to consistently flip the entire cycle. Okay? So take any Hamiltonian cycle in this directed graph, I can trace it in the undirected graph, right? If you went from V to U, I will come from V, you kind of keep going in the right way. But now I have a choice, I can flip everything, but that's the only flip you can do is consistently flip everything. Okay? There are two for every Hamiltonian cycle here, there will be two Hamiltonian cycles here. Traversing this way, traversing it that way, but that's all you have. Okay? Okay? It's a good exercise to check that there is a Hamiltonian cycle in this directed graph if and only if there is a Hamiltonian cycle in this graph, right? It's very important that we add this middle vertex. The Hamiltonian cycle has to kind of go this way. I mean, if you came here and want to visit this, you have to go like this, right? That corresponds to actually the directions, okay? It's interesting to try to convince yourself that this construction works, right? So this is one of the rare examples where we have converted an directed graph problem into an undirected graph problem. The other way is easy, right? Converting an undirected Hamiltonian cycle problem to the directed Hamiltonian cycle problem is easy. Yeah, that's just bidirect the edges that will work. But this is going the other way, so it's kind of interesting, okay? Okay, so that's the construction. One more problem which is very closely related to is called the Hamiltonian path problem, okay? What is the Hamiltonian path problem? I don't have to visit all, I don't have to make a cycle but a path which visits everybody. So start somewhere, find a path which visits everybody. You don't have to come back in a cycle to the starting point. Okay? So why is the Hamiltonian path problem also NP-complete from what we have seen? Okay, you can do it a reduction from Hamiltonian cycle, but okay, now that, what will you change in this reduction? You just remove this back edge, right? Okay? If you remove this one edge, the whole reduction will go through. You'll have a Hamiltonian path if and only if it's a satisfiable. Right? So we just made this go back simply to create a cycle. Okay? So that's one way of looking at it. You can follow the same reduction, except that I don't have this edge, so I have to start here and end up here. That's the only way to create a Hamiltonian path, and the whole reduction goes through. Or you can do other things by reducing Hamiltonian cycle to Hamiltonian path. Right? That's also something. Okay? All right? So it's a problem that you need to know. It's very, very closely related except one. Okay. All right. Let's do coloring, right? What is coloring? We sort of briefly mentioned coloring, right? Last lecture. So I give you a graph and I give you an integer k and I say, can you color this graph with k colors, right? What is a valid coloring? A valid coloring is coloring of the vertices with some number of colors, 1 to k, such that no two adjacent vertices get the same color. So here I am 3 coloring this graph, right? I use 3 colors, right? Red, blue, and green. Yeah. So can you color? 3 coloring problem is, can you color a graph with red, blue, and green such that no edge gets the same color? Right? So equivalently, what is it? What does each color? If I look at all the vertices with the given color, how do they look? They are from independent set, right? Because there cannot be edge. So it is asking, given a graph, can I partition it into 3 independent sets? Right? So when k equal to 2, it's a, what is that? Is a graph bipartite? Can I partition the graph into 2 independent sets? Right? The edges go only between them. When k equal to 3, can I partition it into 3 independent sets? The edges only go between the partitions, right? So k equal to 2, we already kind of mentioned that you can solve in linear time using breadth first search, right? You know, the graph is two colorable if and only if it doesn't have an odd cycle. An odd cycle cannot be colored with two colors, right? If I have a triangle or a pentagon or a, right? If it has three odd cycle, you'll see that you'll get stuck with two colors. You need three colors. So the nice theorem, graph theoretically, is that a graph is two colorable or bipartite if and only if it doesn't have an odd cycle. Okay, so that's easy using BFS. So it turns out that checking whether a graph is three colorable is already NP complete. Okay, all right, and what is this very nice reduction that Karp used? Here is a reduction. I mean, there are many applications of coloring, so I will not go into the applications right now. You can look at it. Okay, here is this beautiful gadget he created, right? So let's see. Can you color? So I force you to. So I look at this graph. Okay, it should remind you of like a circuit of some kind, right? I only give you three colors, right? Red, blue, and green. I force you to color this green and I force you to color this as red. Can you color the rest of the graph using red, blue, and green? No, I mean, I chose these colors for you. You can't, right? So why not? Let's do some enumeration, right? You can say, okay, remember it's a triangle, so I have to use red and blue here, right? Okay, so okay, we can try both possibilities, right? You can say, maybe I should use blue here. Okay, if I use red here, I'm stuck, right? Okay, so I have to use blue here, right? So you say, okay, blue here. Okay, sorry, that's not blue. Okay, so I mean, okay. Okay, so I have to color this blue. And that has to become red, then what happens? Right? I'm stuck, right? You see that I'm stuck? Yeah. So that is red. Okay. All right. Now at least we don't have color, right? Okay. You'll say, okay, this guy should be. Okay, right? You know, because of this, one of this has to be blue and green, right? That's the only choice, right? Okay, but then if I use a blue and green here, then I can get stuck with red, then I'm stuck, right? So I can't color, okay? Okay, good. Yeah, that's easy now. Okay, can I color this? Yeah, you can color this. Okay. So what do the colors signify to you? Right? Okay, think of red as false and green as true. Okay, and this as a circuit. Okay, what this says is that if you color all this as false and you want green here, no choice, no way. Okay, but if you give me at least one green, this will be possible. Think of this as some kind of an OR of these three literals, okay? Okay, so it's saying that if you make all of this false, I can't get true here. Okay, if you make any one of them true, I can get true here. Okay, so he's mapping, in some sense, a small circuit with a small gadget graph. Okay, how he did it, I have no clue, right? But that's the idea, okay? All right, that's the starting point. We still have a long way to go, okay? All right, is it okay? I claim that if for any of this, see, if you want this green, if you give me one green, I can color the rest to make sure that it's okay. But if you make all of them red, there is no way. Yeah? Is that clear? I mean, you can verify, but you know, this is this one is okay. So that's the starting point. So now again, remember, I am trying to do what? I am trying to reduce 3 sat to 3 coloring. What does that mean? Given a 3 CNF formula, I am going to create a graph such that this formula is satisfiable if and only if that graph is 3 colorable. Okay? How am I going to do that? So again, it's very clever. So start with this graph, the base graph. Okay. So it's a bunch of triangles, right? How many triangles? Well, I have a base triangle and one triangle per variable. Yeah, remember my formula has n variables, right? So I'm trying to create a graph out of it. I start with this graph. Yeah? Okay. Now, how many colors do I need to color this graph? I need 3 colors, no? Yeah? Okay. So, well, I know I'm trying to color this graph with 3 colors and I need 3 colors. So let's fix the colors of this base triangle so that it'll make our discussion easy. I mean, I can permute the colors, right? What is red, blue and green? I can swap the colors, right? Without changing anything. So might as well fix, like, I say, okay, this guy is going to be blue, this guy is going to be green, this guy is going to be red. Okay? I'll fix this, okay? What choice then am I left with for the rest of the graph? So every one of these guys has to get red or blue, right? Red or green, right? So that's the idea, right? If you take this triangle and color this green and red, that means V1 is going to be true. If you color this red and green, that means I'm going to make it false. So I see I've encoded how many different colorings are there once I fix this color? 2 to the n, right? How many different 3 colorings are there of this graph once I fix these colors here? Precisely 2 to the n, right? Because for every variable here, I can choose red green or green red independently. Yeah, because that's it. So we already encoded assignments to the variables in the colorings we can get using this. Yeah, right. Now I still haven't done much. I have to add the clauses and right. Yeah, okay. That's where that base graph comes. Okay. So the idea is this, right? I'm going to try to do the OR gate, right? Remember, A or B or C is this gadget. Okay, the formula has, A or B or C where they are literals, right? So I'm going to try to use this gadget to create colorings, right? Right? Okay, so it's okay. So let me tell you the construction, right? So suppose my clause is A or B or C. Remember, A could be a negation to A is a literal here. Okay, it's not just a variable; it's a literal, right? It could be not xi. So I'm going to remember the original graph, right? This one, right? I have this, so I fix that. So I connect base T false to this gadget. So if I fix this to be blue, this to be green, this to be red, and I connect this to both, what should this be? This has to be forced to be green, right? If I want it, assuming I fix this coloring, there's only one choice of this color, green for this guy. Now I construct this gadget, okay? Okay, remember the property we had. If you make all this red, can I get green here? No, right? Okay, so if you make all this false, you will not be able to get green here. Okay, so I'm saying this graph, if you assume that these colors are fixed, the only way to 3-color this graph is to make at least one of these guys green. Is that clear? Okay. Assuming this coloring is fixed, the only way to color this graph with 3 colors is to make at least one of these colors green. Okay. If you make all this red, there is no way to color this guy green. Okay. Yeah. Okay. Okay. All right. So this is the construction. Okay. So it's actually very nice and simple, but it looks complicated because it is complicated. Okay. I mean, in the sense that drawing it is complicated. The idea is actually simple, right? Okay. We have how many? We have 2 clauses here, right? Okay. Okay. What is the starting point? Okay. Let me see if I had another graph. Let me see if. Is this better? Okay, not any better. Okay, let me see. Okay, let me say it this way, right? You start with this, okay? For every clause, you add a gadget like the OR gadget, and connect the inputs of that OR gadget to the literals that are in that clause. Okay, so let's see that. Okay, it's very mysterious how he came up with it, but okay. This, remember, what was our starting thing? We had many triangles, right? One per variable. Okay, so here is that base triangle, true, false base, right? And these are the triangles for the variables. Yeah, how many variables do you have? U, V, W, X, Y, 5 variables, right? Okay, so the 5 triangles are connected like this, right? Labeled with not U, U, not V, V, not W, W, not X. That was the base graph. Okay, now for each clause we do what? We create that OR gadget. Okay, how do we create the OR gadget? Remember, this is the OR gadget, right? So the inputs to the OR gadget, this is for clause U, not V, W. The inputs for the OR gadget are U, not V, and W. Yeah. So this is the OR gadget for the clause U or not V or W, right? Let's look at the inputs. What are the inputs to the OR gadget? U, not V, and W. Okay. And what about this clause? We create another OR gadget, and the inputs are V, okay, V, X, not Y. Okay. All right. Okay. My claim is, and this whole graph is 3 colorable if and only if this formula is satisfiable. Okay. Okay. Let's see why this if you give me a satisfying assignment, I'll 3 color it for you. Okay. Okay. Remember, we fixed this to be what? This is red, right? Yeah. So give me a satisfying assignment to this formula. Give me a satisfying assignment. It's not hard, right? U equals to true, say, V equals to true, W equals to true, right? X false, say Y false. Is that okay? Yeah? Some random assignment, right? So how can I use that assignment to color this guy? Remember, we fixed this, right? What is this? This is blue, and what is this is green, right? Okay. Well, what choice do we have? Once we have this, remember, this guy is connected, OR gadget is connected to both blue and red, right? So the only choice for this vertex is what? Green, right? Yeah. So we don't choice here. So this is green, this is green. If you want to fix these colors, then you get green here, which means that we want to make sure both clauses are true, right? Okay. So let's assign the red and green to these variables. So remember, because this blue is connected to both of these, the only choice we have is red green or green red, right? So based on the assignment, we'll do that, right? So let's see. Let's do the green, right? U is green, V is green, W is green, not X is green, Y is green. Yeah? Okay. And then red, okay. The rest have to be red, right? Because there's no choice. Okay. 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 Now we have to fill this, can we fill this OR gadget? Why? Because this guy is green, and we said that we can color this gadget only if at least one of these 3 inputs is green, right? Otherwise we can't color this gadget. Are the input this guy is green, so he has 1 green, 1 red, and 1 more green. So we can color these guys. Yeah. And similarly, this guy has 1 red, 1 green, another green, so we can color this. Okay, right? Okay, now if you say, what if I gave you a bad assignment which doesn't satisfy it, then, if these guys are not in, if the clause doesn't have at least 1 green, there is no way to color this graph. Okay, all right? Okay. Alternatively, if you give me a 3 coloring of this graph, I'll show you how to get the assignment to this formula. How can you 3 color this graph? If you fix this to be blue, green and red, then the choice for these guys is green, right? Okay. Then my claim is, if at least for this gadget, if at least one of the inputs is not green, then there is no way to color this graph, right? And so you would know, I mean, looking at these colors of these variables, you would know what the assignment is. Okay. So that's the idea. Okay. Again, it's not completely easy if you don't spend some time on the reduction, right? Okay. Rough idea, right? Okay. It's a clever reduction. It takes some time to absorb it, right? But you can color this graph if and only if this formula is satisfied. Yeah. And it's easy. The graph itself is easy to construct once you know how to do it, right? I mean, what I described. Yeah. That's the gadget reduction. Yeah. Very clever. So it also shares the same something fundamentally. It is not obvious a priori that somehow 3 coloring a graph can encode something like satisfiability, right? And it is, the probability of anybody randomly coming up with this very clever reduction is very low, right? That it requires a very careful construction. So what does it tell us, right? A lot of people say, oh, there is no way in practice anybody will come up with this kind of graph to color, right? And this is a very delicate construction which reduces satisfiability to the very intricate way to this graph, and what is the probability that somebody will actually generate such a graph? Okay, but the answer to that is the following. The fact that a problem is hard means what? It is hard in the worst case, right? You can have any heuristic you want and they may do very well in practice on some classes of instances. The thing when problem is hard in the worst case, what it means is that you don't have a provably correct algorithm on all instances, right? It's a lack of robustness. It doesn't mean that all the problems in practice are hard. It just is a saying that, okay, look, the reason why we don't care about sorting in practice and theory is that it is a solved problem both in theory and practice, right? It actually works well. We don't worry about it because it's easy, right? If you had a problem where, sometimes the algorithm gave up on you, it's not so nice, right? So you don't have robustness. So worst case intractability should not be taken as that all the problems in the real world are going to be hard. It's simply that we don't have a robust algorithm, right? Which works in all instances nicely, right? That's what it means. Okay, all right, that's the 3 coloring. What you need to know is that, what is 3 coloring, right? And okay. The last thing, is circuit sat, and this is to kind of give you a sense of why the Cook-Levin theorem is maybe more plausible. Okay, so some of you have asked on PRs, right? Why should I create? SAT seems like a restricted formula. Why don't you let me use a different formula, right? A Boolean formula, arbitrary Boolean formula, right? Why not, right? And the answer is, that just to kind of give you practice, but it's not for any technical reason. So let's see circuits, right? Circuits are more powerful. What is a circuit? Everybody knows what a circuit is intuitively, right? But formally, what is a circuit? In a graph theoretic sense, right? A circuit has some inputs, right? And it has gates, right? Yeah. Okay, and the gates are connected to each other, right? Okay, what kind of gates? We have 3 types of gates, right? NOT gate, OR gate, and AND gate. And the inputs of the output of one gate can be an input of another gate. Okay, and you don't want cycles, right? You don't want the input of one to be the output of another, and output of another to the input of another. Then it doesn't make sense as a circuit. So we have a directed acyclic graph on these variables and gates, right? We have a bunch of nodes, we have a graph, right? The graph represents the circuit, right? And a single output gate, and each gate has, depending on whether it's an on, and or it has 2 inputs, and if it's a NOT gate, it has only 1 input, and the edges represent the connections, right? the output of one going to the input of another, and then we have some input gates, right? The input variables. Okay, that's the circuit, right? The circuit is represented by the directed acyclic graph, right? Okay, so now what is if you look at this circuit, some of these are 1, some of these are 0, but some of the inputs have question marks, right? So these are the variables of the circuit SAT problem, right? So what is the circuit SAT problem? I give you a circuit like this and I ask you, can you put zeros and ones on these question marks so that the circuit will evaluate to true? Okay, I give you a circuit like this and say, can you make this circuit evaluate to true by putting zeros and ones in these question marks? This looks like SAT, right? Sort of, yeah. Except it's more rich, right? Because I'm allowing you arbitrary circuits, right? You can compose them in any way you want, right? You can use ands, nots, and I'm not constraining you to use SAT formulas, CNF formulas, yeah? Yeah? Okay, is this more general than SAT or less general than SAT? Sorry? Okay, so what does it mean? How can you say that it's more general than SAT? What is a formal way of saying it? Can you reduce SAT to circuit SAT? Yeah? Okay, so more formally, if I give you a formula like this, can you create a circuit from this with question marks such that the formula is satisfiable if and only that circuit evaluates to true? How will you create a circuit from this? Yeah? How will you create a circuit from this? Very simple circuit from SAT. That the circuit should be true if and only if this formula is satisfiable. If you can, what are the inputs to the circuit? Is it okay? Shall we create a circuit from this? Yeah? What are the inputs? The variables are what? The variables of the SAT formula, right? How many are there? So, okay. So we have x1, x2, x3, x4, right? Okay. So we have for each clause, okay, let's don't worry about degree 2, right? Let's say an AND can take any number of inputs, right? We'll worry about that later, right? So what are we really saying, right? You know, we want something like this, right? The idea is, you know, we create a OR gate and then we create an AND gate, right? Yeah? What does the AND represent? The AND represents that all these clauses have to be true, right? What does the OR gate represent? You know, what should we connect to it? Okay, what are the inputs to the OR gate? X1. So this is the first clause, right? X4, yeah? Okay, what about the second one? X1. You have to have a NOT gate, right? And goes to that one. So this one also I need a NOT gate, and then it goes to, okay, and so on, right? You know, yeah. I mean, okay. You see that this circuit is precisely satisfiable if and only that, yeah. Circuits are more powerful than CNF formulas, right? The only thing is, you know, I have an AND gate with 3 inputs which I can easily take 2 at a time, right? Yeah? Okay, the OR gate also, it has 3, but I can make it 2 at a time, yeah? Agreed? So you can easily reduce SAT to circuit SAT, right? Circuits are much more powerful, yeah? You can easily see why, you know. Okay, but what we can also do is go the other way, which is also interesting. Okay, it's kind of useful to see how you can take a circuit and go to SAT. Okay, how will you go from circuit to a SAT? So, okay, I want to take this circuit and create a formula so that the formula is satisfiable, the CNF formula is satisfiable if and only if the circuit is satisfiable. Okay, that's kind of useful Boolean logic to try. What should the variables be? The variables should be these corresponding to the question marks, right? Yeah. But how do we encode the computation of the circuit using just CNF formulas? Okay. Okay. We want to also have a variable for each output of the gate. Okay. For each gate, we create a new variable. Okay. All right. So here is, I'll use pictorially. So this is one which is a fixed thing. XA, XB, XC, XD, XE, and I have a label these nodes, and I have XF. So I have how many variables? The number of nodes in the circuit, right? Now, what does it mean that this circuit is satisfiable, right? Okay, let's write all the constraints that must be satisfied by the circuit. Okay, what is the meaning of XF? If you think of the meaning of XF, XF is the output of this gate, right? But what is it that we want to represent in that? XF is the AND of these XA and XB, right? Okay, let's write down all those equations. Okay, so this is what we write, right? What do we know? XA is 1, XD is 0. What is XF? XF is equal to XA and XB, right? And XG is equal to what? XB or XC, right? And XH is equal to XD and or XE, and so on, right? XI is what? It's a knot of XF, right? And then we want to make sure that XK is true. Yeah? Okay? All right. So if I write down as equations, asking whether the circuit is satisfiable is simply saying, is there an assignment to all these variables such that all these equations are true, right? Is that clear? Yeah? Okay, now is this in the nice form that we want? Not really, right? It's equalities, right? Okay, but that's very easy. What he's saying is that this circuit is satisfiable if and only if there is a Boolean assignment to these variables such that all these equations are true. Okay, so it's an AND of equations, right? Okay, but these equations are Boolean equations with just 3 variables, so you can easily write them in CNF form. Okay, so what do we do? Okay, this is just a way to say that if you have an equation of the form xj is xg and xh, you can equivalently write it in these 3 clauses, right? Any Boolean function can be written in CNF form, but the size of that might be exponential. But here, the Boolean formula is only on 3 variables, so we don't care if it is exponential, right? We are doing it locally, right? This is just an equation among three variables. So we can easily express it in CNF form. It doesn't matter, it is exponential in 3 is fine, right? Okay? Yeah? So that's it, so we take all this, we write all these equations, and we say each equation, I can represent it as a bunch of clauses, right? So this equation is true if and only if this formula is true. Okay, you can verify that. Okay? Any Boolean function, you can take a truth table and write it down as a CNF formula. Okay? So I'm doing it for 3 variables at a time, and because it's only 3 variables, the formula size will be maybe at most 8 or so, right? And we can do some optimization, and that's it. So you take this circuit, you write it as these equations with the variables as for each gate, and then you convert each equation into a bunch of clauses, and you take all the AND of those. So you have converted a circuit into a formula, right? Right? Yeah. Yeah, because what did we do, right? We took a graph. We created 1 variable per node, right? And for each node, I wrote down 1 equation, right, which is based on the gap, right? Because remember it's a circuit, so it has only 2 inputs and 1 output, so it's all. And then, now I have a bunch of equations like this. That's easy to write. And now the only thing I have to do is, how can I convert an equation of this type into clauses? But remember, they're all on 3 variables, and I will only get 4. I mean, I'm giving you a table specialized to this instance, but if I have XA equals to XB or XC, I can convert it mechanically into 4 clauses. So I mean, I'm just converting into everything mechanical. Yeah, so that's easy to see as polynomial type, right? Okay, so that's it. I can go from circuit SAT to SAT, and SAT to circuit SAT is also easy, right? So what does circuit SAT give you? More flexibility in doing reductions, right? Or to convert things, right? It's a language, right? That's why we use circuits in our computers, right? It's easy to write, develop circuits. Okay, so you've seen a bunch of NP-complete problems, right? And so you need to know this list, okay, to do reductions. So SAT, 3-SAT, circuit SAT, right? These are logical problems, very powerful modeling problems, right? And you need to know independent set, clique, and vertex cover, Hamiltonian cycle and Hamiltonian path in both directed and undirected graphs, 3 coloring and coloring. Coloring is given G and K is graph G colorable with K colors. Okay. So once you have this set, you can try to use those for reductions, right? The known NP-complete problems are huge number. We know a lot of NP-complete problems by now, right? So when you have a new problem, you try to choose a problem that is hard, known problem that is hard, that is as close to it as possible. What is as close? You know, that's not a formal definition, but something that is reasonably syntactically or somehow similar, right? But obviously that's an infinite set, and we can't make you learn all those kinds of things, but we will give you problems which are related to these kind of problems. So you should know this small set so that you can use any of those things to reduce to your new problem, right? Okay, like I can give you the balloon and say, what does the balloon look like? Okay, right? You have to say, okay, does it look like SAT? Okay, that may be hard, right? So that's the thing you have to kind of get a bit of hang of, right? What should I use? And one simple strategy is to walk down the list. So, is this right? And I'll give you this list in the exam. You don't have to memorize this list, right? I'll tell you what this problem is, right? But you still have to have some understanding of these problems, of what the structure is, otherwise you won't be able to do the reduction, right? Okay? Okay? So this is it for NP-completeness. And next lecture I will do, I'll review undecidability and prove Rice's theorem, and that will be the end of the content, okay? And then next Tuesday's lecture will be just review. So I'm going to do the course evaluations next lecture. So I will make an announcement on Piazza about that.